Good morning, everybody. My name is Mark Bunch, and I'm going to be your host for this morning's webinar on HAZID, the Hazard Identification Study. I noticed from the dashboard that we've still got a few people joining as we go along. So if it's okay with you, we'll start in a couple of minutes or so. So if you just bear with us for that time, then we'll make a start. Thanks very much. I shall talk to you soon. Okay, I think we've got more or less everybody that we're going to get this morning. So good morning and thank you very much for joining me. It's rather rainy here, so I hope it's a little bit better wherever you are. My name is Mark Bunch and I'm one of the senior consultants with Sigma-HSE, who are a consultancy based out of Winchester in the south of England. And this morning the webinar is concerned with the Hazard Identification Study, or the HAZID. It's I think at least one of the most powerful tools for hazard and risk assessment at our disposal, because it is rigorous and yet one of the less resource intensive studies that you can do to demonstrate that your risks are as low as reasonably practicable. So the way we've structured this particular webinar, if I can get my mouse to move, is as follows. So I shall start with an introduction to the company, Sigma itself, and then I'll describe how hazard and risk assessment work, and why really you should think about doing the hazard before other forms of risk assessment. And we'll look at that from 2 points of view. One where you've got a new plant or a new design that you wish to assess, and the other one where you've got an existing plant. Because the technique itself lends itself extremely well to both those scenarios, but with a slightly different emphasis. So I shall try and draw that out for you. And then it'll be a question of where does the hazard fit in with the life cycle of your plant, and how you would go about conducting a hazard. And we split that up into how you would record it, the deviations that we choose and use and why they are appropriate, and then some more on the detail. So what causes we might expect for a particular deviation from the design intent, the scenarios, how we develop those, what consequences mean in terms of damage to people, damage to the environment, and indeed damage to your company's reputation. A couple of slides on risk, how we actually go about assigning a risk level to a particular scenario, because very often the bits that people get wrong. A lot of you will have an existing risk matrix or something of that sort that tells you how to do that, but many people don't, and they use the guidance that's available, at least in the UK, from the HSE. So I should show you how that fits in with the way that we conduct hazard assessments and how you might go about doing that yourselves. Safeguards, we shall say a few words about safeguards once we've done the risk, because if you don't know what the risk is, you don't know how good your safeguards need to be. So actually calculating the risk gives you a very good indicator as to what layers of protection, as to what safeguards need to be in place. And that's part of the decision making. It's one of the strengths of the technique. and it shows you where you've got gaps, either in your protection or in your knowledge. And once we've done that, we're able to assess how good they are. And that's one of the key things as well. That tells you where you're spending your money, and it tells you where you're getting best value for that money in terms of the risk reduction. So it's a very, very useful thing to do. And then finally, at least in the UK again, we are in a position where we are goal setting. We try to improve year on year, and part of that continual improvement is to review and revise the hazard over time. And that's to take into account changes that you will impose on your plant, either a major change that goes through something like your management change process, but it also covers you for things like the cumulative effect of many small changes that may accrue over time. So that's the way we're going to structure this morning's talk. And I'll start off with this introduction to Sigma-HSE. We are a process safety and consultancy, but we have three main tranches, or three main areas of focus. We have our consultancy itself, conducting studies like HAZIDs and HAZOPs and LOPAs and failure mode effects analysis and all the other gamut. We have expertise in all of those. We have an extensive testing laboratory as well, for reactive chemistry, combustible properties, flammable properties of your materials as well. And we have a training arm also, of which webinars are, I suppose, one of the ways in which we do this. But we will offer bespoke training courses on things like dangerous substances and explosive atmospheres regulation, HAZOP, HAZID, LOPA again, we can do all of those. All of which keeps us very, very busy, I can assure you. We are pretty well worldwide at the moment as well, which is quite nice. We have offices in Delhi and Mumbai in India, and Hyderabad as well, Winchester in the UK, where our headquarters are, and we have recently opened an office in United States also. And our laboratories are based in Winchester, New Delhi, and, well, again, in the UK at something called eLab, our environmental testing laboratory. In terms of consultancy, well, we run the gamut, really: process safety management, fire and explosion hazards, electrostatic assessments, PHAs, the process hazard analysis, of which HAZID is one example, functional safety, and so on. And in laboratories, people far more clever than I are dealing with the testing of powders for combustible properties, their fire and explosion properties, gas and vapor properties, chemical reaction testing. That's the one that always gets me. It's quite complicated, is that. So I shall now take you through what the HAZID is and how it fits into your PHA program, really. So this is the section titled Hazard and Risk Assessment. We need to know, first of all, what a hazard is. Now, a hazard, it means different things to different people. It very often depends who you ask. But in our business, we have a definition, and a good one at that, because it captures the salient point. We have, from our regulations, the 94 regulations on occupational health and safety. These are an example regulations. It's also used in the management of health and safety at work regulations as well. So it is across the legal board, but it means the potential to cause injury or illness. And the important word to bear in mind there is potential. It doesn't have to be realized, but if the potential is there for harm to occur, then we regard that as a hazard. And in the process industries, at least, that's any activity, any procedure, any plant, a process, a substance, a situation, or other circumstance that has that potential to cause harm. That can be to the environment, it can be to people, and although it's not encapsulated in the law, you may well want to think about it in terms of the damage to your reputation as well. So the HAZID itself, and here's a reasonably succinct definition for you, a form of process hazard analysis, we're identifying all reasonably foreseeable hazards at a facility that may cause an undesired outcome. And the outcomes that we're mainly interested in are those that lead to a major accident. And the major accidents are typically those that will cause at least one fatality, but more frequently have the potential to cause more than one fatality. So these are to do with fires, explosions, the release of toxic material where you have a large number of people or multiples of people whom you can hurt. So we identify what those are, and doing that, we're not so much looking at the slips, trips and falls aspect of safety, the so-called occupational safety. We're looking at the process safety features. And you can think of those simply in those terms of a loss of containment of a hazardous substance, one that has the potential to cause harm, where that harm can be realized in the form of a toxic release, hurting people, fires and explosions. And in doing so, it helps to identify what safeguards need to be in place, either the ones that you have or the ones that you don't have, and therefore are a gap in your protection. So if you can do that, you can fill that gap, and that means that ultimately you end up with a safer plant as a result. Whether you've got hazardous substances or not, we can check. We can look, first of all, the classification of dangerous substances, what substances you have on site. And first of all, we look at how much you have. The more you have of a particular substance, the more harm you can do with it. But it doesn't rely just on the quantity, it's also the quantity plus its physical properties. So if you have nickel, for example, nickel is relatively benign in an ingot form, and you can drop it on your foot and hurt yourself. But if you have it in an inhalable form, as a dust or a powder, then it can do you some very serious damage indeed. And of course, it's a lot harder to keep tabs on in that particular form. So it's the way you handle these substances as well, whether they're solids, liquids, gases, and the conditions under which you handle them. Lukewarm water is all very well to be handled. We don't tend to do much harm with that. However, steam is considerably more hazardous. So the conditions of pressure and temperature under which you do your processing all have a potential impact on how hazardous your materials end up being and what the consequences might be if you actually lose track of it and have a loss of containment. Whether a substance is hazardous or not depends very much on its chemical properties. And the ones that we're mostly interested in at the moment are whether it's explosive, an oxidizer, and one of the three categories of flammability as well, but also its toxic properties also, whether it's immediately dangerous to health at a certain level, or whether it's got further long-term effects on people, or whether it may cause harm to the unborn child, things like that. And we can classify in terms of the damage that these substances can do to the environment. So whether it's damaging to aquatic life, if it gets into a watercourse, whether it's damaging to land use, gets into the air, or its effect on biodiversity, so flora and fauna, flowers and plants, whether you've got the potential to hurt any protected species or any natural habitats that might be close to you as well. So all those things we need to take into account when we're conducting the hazard, because those are the things that constitute a major accident. Those are the things that we need to have safeguards against. And of course, we can do damage to people as well. We're looking at fatalities, injuries, even health and psychological effects, whether that be in the short or indeed the long term as well. The effect on the environment I've just mentioned, and you may want to think in terms of the effect to your business. So it's worth considering, for example, what size of release and accident you could have before you didn't have a business to return to, whether it's going to do your damage, that your reputation, so much damage that people don't actually want to do business with you, including other companies, your employees, your customers, your neighbors, for example. So we can do damage to the environment, we can do damage to plant, we can have a consequential business loss as a result of that, and ultimately a damage to your reputation. And we see that frequently. We've seen that in cases in the past, for example, Union Carbide, after the Bhopal disaster, and the intense dip in share price from BP after both the Texas City accident and the Macondo oil spill, the Gulf of Mexico oil spill, how they weren't taken over as a result of that drop in share price, I'll never know, but there we go. So we have a means, we have several means, in fact, at our disposal to identify where these major accidents may occur, and how to go about identifying what our safeguards should be. HAZOP and HAZID are two very common ones that are used in the process industries. We also have things like what-if studies, failure mode effects analysis, which is the FMEA that you say there, simple checklists, people's experience, and this is one that frequently companies miss out, learning from past incidents. They don't have to be your own past incidents. They can be other people's as well. It's always said that a wise man learns from his mistakes, but I think a wiser man learns from the mistakes of others as well. So the use of past incidents and things like the loss prevention bulletin, sharing experience across companies and across industries is very, very useful indeed. It allows us to learn from the mistakes of others. So why HAZID? In the UK, we have a safety report to produce if you are a COMA site, and a top tier COMA site as well. And that's one set of, essentially it's the process safety regulations in the UK. And the HAZID is a very good way of demonstrating that you are undertaking a fit and appropriate risk assessment. There is a legal requirement to identify all major accidents and their related causes using some form of rigorous, systematic approach, and one that is documented as well, because you have to show this to the regulator to demonstrate that you have reduced your risks to the lowest possible level. And HAZID is good for this because it's simple, it's relatively quick, and it works on an order of magnitude basis rather than going to the far end of identifying all the numbers. You can do it as an order of magnitude type approach, so it's more qualitative. And that means that it's less resource intensive, and it's suitable for personnel at all levels in the organization. So whether it be managers, whether it be engineers, whether it be operators, whether it be the purchasing, everybody can get involved in this sort of thing. And it's a very good learning learning exercise as well. You learn a great deal about your plant, so it's useful for training. The results should be or must be reflected in your risk assessment, your safety management system, and the adoption of your control measures. When we identify safeguards in the HAZID, those automatically become important to you. So it should be documented that they are important, and they should be treated as being special. It should be rigorously maintained and looked after so that you can rely on them as a safeguard against any particular major accident that you've been able to identify in the HAZID. So it is a very useful tool in all respects. Shows you where you're spending your money, shows you what your safeguards are, and therefore identifies what needs to be done in order to maintain your risk levels at as low a possible level. So when is it appropriate to do it? And I've identified two possible reasons why it would be your first approach to hazard identification. The first one is where you've got a new plant or a new design that you're about to implement, and the other one is where you've got an existing plant. So the technique is exactly the same, the steps that you go through is exactly the same in both those cases, but the results are different, and the results can be applied differently. So I shall show you how those fit together. First of all, we'll look at the new plant and design, and I'll start by showing this sort of summary. We sometimes call this the cradle to grave model, or the life cycle model. And it works in a reasonably straightforward manner. If we have a new plant, so I hope you can see my my cursor going around new plant there up in the top left corner. The first thing we need to do is to identify the hazards. Now, if it is a new plant and all you've got is a rough idea that you would like to make, for example, some chlorine somewhere, well, you don't have very much detail that sits behind that when it's just an idea. But you do know certain things about chlorine. You know that it is toxic, you know it's denser than air, and that can be used to inform your design somewhat. At least you'll know that if it is toxic, it's a good idea to put it in a place that's not terribly crowded, for example, because a loss of containment would involve a lot of people. So we can at least make some early decisions. Once we've got a process that we're looking at, once you've got something like a process flow diagram or a block diagram that might consist of, you know, just boxes saying this is the reaction stage, this is the separation stage, this is the final product storage stage, we can start to put some detail into that. If you know the conditions of temperature and pressure and what sort of flow rates you're looking at, you can then interrogate that design, and the hazard is the point at which this is most appropriate, because it is appropriate for the level of detail that you have about that design at the time. It informs the design, it allows you to make better decisions as a result of that, shows you what additional safeguards might be needed. And that's why we've got the feedback loop here. So the hazard will inform the design can then go back for another hazard evaluation, and so on and so on. We go around this loop. Once we've got a design, we'll do something like a HAZOP study, which is a more detailed line-by-line study. And once we're happy that the design is as safe as we can get it, we can go into construction. Once we've constructed our plant, we can do the operation. Once we've operated it, we'll do some inspection, some maintenance certainly on the safeguards that we've been able to identify thus far. And we will do the verification. And the reason for doing that is because change happens. Either internal change through your management of change system, or changes in personnel, changes in training and competence, for example, all have an effect, because they affect not only what you do, but also the way that those safeguards are implemented as well. And change doesn't have to be inflicted upon you internally. It can be inflicted upon you from outside as well. So there can be changes in legislation, changes in what you are required to do under the law, and changes because we've learned some lessons from others as well, maybe internally, maybe externally. But that allows you to verify your hazard has picked up everything that it is supposed to have picked up, and that your risk profile remains as low as it can be. So the reason for doing hazard early in this study is because it is relevant to the level of design, the level of information, the level of detail that you have early on in your new plant. So it's appropriate to do it then. And then as the detail of that design is bottomed out, you can go into more in-depth, less abstract styles of studies. So it is the level of abstraction that's important. We are at a higher level with the hazard than you are with a HAZOP. It does not go into the levels of detail, but it gives you the major accidents. And that's the idea. If you can get rid of those early on in your process through either eliminating a hazardous material or changing it to something else, reducing quantities, those are all so much easier to do at an early stage in your design process. It's appropriate for that level of design information, and it provides good information for any other risk assessments that you do later on. Therefore, it identifies any gaps. If you know, for example, that a plant is heavily manually operated, and that all your scenarios for a loss of containment are to do with a human error because it is manually operated, it will point you in the direction that maybe some specific study aimed at reducing human error would be appropriate. Equally, if it was an automated plant and all your scenarios are to do with failures of that automation, level transmitters, temperature transmitters, and so on, or even the control system itself, it might point you in the direction of doing another study into functional safety to reduce those risks there. So it is good for identifying where those gaps arise. For an existing design, going back to the life cycle model again, it is a good thing to do because of its lower use of resource. So whereby a HAZOP, which you should be thinking of redoing every 5 years or so, the HAZID, because it is less specific, it's more abstract, I should say. It's nonetheless rigorous. You can do it in far less time. Therefore, you can review much more frequently. And as I say, it has other benefits as well in terms of its usefulness in training exercises. If you get the operators involved, it suddenly becomes apparent to them why they are being asked to behave in a certain way, why they are being asked to do things in a certain order, because those major accidents are brought up full and foremost. It uses fewer resources. So all this stuff remains true. It's high level on a HAZOP aimed at the major accidents, but it uses fewer resources to determine where those additional safety studies might be required. Now, because HAZID is a very good precursor, it feeds in neatly into more specific studies later on, whilst still giving you all that vital information about what your major accidents are and what your safeguards need to be and how robust they need to be. Because that is all true, it allows very good alignment of those studies with your site's overall process safety management structure. So any good process safety management system should have or should cover things like whether functional safety is required, risk assessment, maintenance activities, all the rest of it, human reliability, even procurement should be in there. Anything that you have in your system that reduces the likelihood or the severity of accidents. And it's all very neatly tied together in the HAZID because of its level of abstraction. It summarizes the effects of all those things to allow the demonstration of any shortfall as well. So if you have existing LOPAs, those will be cited as safeguards in your HAZID, and therefore it ties them all together and summarizes where you might have any gaps also to allow you to fill those gaps. And critically, it shows you if those systems are actually doing the job they're intended to do, and therefore it's whether your PSM system, your process safety management system, is functioning as it should. And this is vital information for management, because without that information, without the demonstration of whether your process safety management system is working or not, the temptation is not to resort as it should be resourced. So not to put the money in where it is actually needed. It shows you where reductions in funding, cuts or efficiencies that management might want to make may have a detrimental effect on process safety, whether it makes the loss of containment more or less likely. So it's a good tool to put in front of management to be able to say to them, this is why we need to resource this in a particular way, because this is the effect that it has on our overall safety performance. So I would use it in that way. If there's ever a conversation going on about where our resources need to be applied, this is a good tool to make sure that any allocations are done with safety in mind. So I'll summarize how we actually conduct the HAZID over at Sigma-HSE. It's a fairly common technique. It's just that we do it in a way that we think benefits clients. This is the added value. I'll take you through it, and you can see how it fits together. So we have some requirements. If you come to us and ask us to do a HAZID, we'll ask you to provide us with a team. And really, we're at your mercy. We're only as good as the information that your team is able to give us. So they are critical to the whole process. We summarised it as personnel with suitable skills and experience. And by that we mean people like engineers, people who are responsible for safety on site. But the most important person in the room, as I usually put it, is the operator. The operator knows how the plant operates in practice rather than how it was supposed to operate, if you see what I mean. So it's very often that we'll get an engineer, and it's usually the process engineer, who will take us through a drawing, and he'll say, yes, we pump from here down to this tank, we open that valve, close that valve, etc. And the operator says, no, we don't. We don't pump it anymore, we blow it through with nitrogen. That change has been in place for the last 7 years. That valve sticks, so we always use the other valve and then route around it, or something of that sort, and everybody learns a little something that way, including the engineers. So the operator, somebody who knows how the plant operates in practice, is absolutely vital to have in the room. It should be a well-managed, a formalized approach with all the appropriate documentation. If you ask me to do it, it will be well-managed, I promise you. It is a formal approach that we use, and the documentation, we use a spreadsheet to record it in. But certainly if you're working in the UK, you need to document your risk assessment. And ideally, we should have some training in the methodology for people who are going to attend as well. If that hasn't been formally delivered, I usually start with a quick 45-minute presentation, very similar to the one that you're looking at, on how HAZID works and what sort of information we are expecting people to furnish us with. We'll need some documentation, and different companies call their different documents by different names. They reside in different systems, but it's documentation to an end, and these are the ends that we're looking for. We need to be able to understand and describe things, and we do that with whatever documentation you have that gives us that information. So we need to know what the hazards are. So those will be things like material safety data sheets. It might be your own testing data that gives us that kind of information. So whatever you've got that does that. We need to be able to describe what the process is and the procedures that you've got for doing that as well. We need to be able to know what the equipment is, what it is designed for, what are the conditions of temperature, pressure, etc., for which your equipment is going to operate, for which it's been designed to accommodate. We need to know what protective devices are there. We need to know, from the point of view of what the consequences are going to be, who we're going to hurt. The people, what assets, the environment that might be affected by your operations. We'll need to know what the frequency that event may occur at and whether that resultant risk is acceptable. Now, you don't furnish us with these two last bits of information. That's what falls out of the hazard. But all these ones, the hazards, the process and procedures, the equipment, devices, and what can be affected, that's all for you to tell us, because that allows us to evaluate what the risk is. So, like anything, there's a flow chart. All good procedures have a flow chart to back them up. We'll need to know, first of all, what it is that we're looking at. So we need a boundary, we need a scope to look at. And within that scope, we'll have a description. And this description, we call the system description here, but it is just a high-level description of what processing it is you do within those boundaries. It is the safe operating envelope, the conditions of temperature, pressure, flow rate, pH, Wobby number, whatever it happens to be, for which your equipment has been designed to operate. We make the assumption that no hazards arise from your equipment operating as it is intended to operate. We'll divide that system into sections. We'll do the analysis on each section and record all the hazards that we can identify. Those will go into a hazard register, and out of that we'll implement some actions, and then we'll review after a time period or if there's been some change. So that's the very high level description. Getting a little bit more granular, once we've selected a system, the way we do this is to first of all select a deviation. I'll show you what the deviations that we use are, but they're to do with excursions from your safe operating envelope. It's when you don't have the pressure that you're looking for. It's when you don't have the temperature that you're looking for. Can that occur And is it going to give you a problem? So once we've selected our deviation, I shall ask the team what the causes are for that. What is the initiating event that gives us the deviation? If we can't think of any, we'll move on. But very often we can think of them. We'll fully describe the scenario. And as far as possible, please do this in complete sentences rather than just abbreviations and acronyms and so on, because people have to revisit this in 3-5 years' time. And it's much easier to do if it's all written down in full English, well, whatever language you're working in, but make it as easy as possible for the reviewer. We'll then look to record the worst case consequence. And this is the one area where clients have the biggest trouble. A lot of them are very reluctant to put in death and destruction as a consequence because they don't want to think of it in those terms. Nobody wants these things to happen, but we have to. It's the reason that you've got the safeguards in place, and if we don't record that, you don't tell the story. It's a narrative that you're telling. These are the hazards, these are the causes, these are the safeguards, and therefore this is why our plant is safe. So don't discount things. Don't say that this isn't going to happen because we've got a control system that looks after it and it's not going to have a loss of containment. We have to go for the worst case consequence without any of those safeguards being in place. What happens if you have a high pressure in this vessel that causes it to fail and you have a loss of containment without looking at the fact you've got a relief valve on there, or without looking at the fact that you've got a high integrity pressure protection system, or whatever else it is you have? It has to be the worst case unmitigated consequence. That allows us to allocate a raw risk or an estimate of risk before any of the safeguards are taken into account. We'll then ask you what the safeguards are that you've got to prevent that from happening, and then we will assess for the residual risk. That tells you what risk reduction has occurred by those safeguards, how good they are, whether you need any others. That's where the gap arises. And if we think there is a gap, we'll record an action. And then once you've implemented the action, you should find that your risks are subsequently reduced. So that's the sort of overall flow sheet approach to HAZID. And we record it on something that would look like this. So I'm gratified to see that I can actually read that as well. I sat on my glasses the other day and I'm on a spare pair, but I can actually read it, so I'm very happy. We divide it into 3 main sections. So there's a section for defining the scenario, a section for defining the safeguards, and a section for defining the recording, so the actions. In the deviation, we will pick one. And the ones that we normally use are over or under pressure, over or under temperature, overfilling, loss of utilities. There are others as well, losses of containment due to things like impact damage, those kind of things as well. But it's anywhere really that you could get a loss of containment, because as long as it's within the equipment, it shouldn't be too much of a problem for you. We'll then say, are there any causes for this? And it could be runaway reaction, could be a pump not working, or deadheading, or a high back pressure, something of that sort. But it's your expertise that tells us what this is, along with the process description. We will then describe the events. So this is the chain of events that leads up to the loss of containment in the hazard scenario bit. And again, this is the bit where we need to record it in as clear a manner as possible, because these things do have to be reviewed a little later on. We will then record the worst case and mitigated consequences in there. So that defines the scenario, from deviation, from an overpressure, what the cause is, what the scenario is, and what we might expect if nothing else were in place to stop it happening or to mitigate the consequences. Then we can score for risk, and that we will do in terms of its severity and in terms of the likelihood as well. The safeguards are next. We have divided this. I usually term this as design features, this first one. So things about the design that means something is not going to happen or is less likely to happen. And an example might be a reactor. The scenario might be an overpressure in the reactor due to a reaction runaway. And you might get an increase in pressure and temperature in your reactor. and the pressure, let's say, goes up to 7 bar, but the vessel itself is designed for 10 bar. So it's not going to explode as a result. That's a feature of the design that means that you're not going to get the consequence. So that would be an example of a design feature that we could cite there as being important. And of course, now that it's in that box, it means that you have to make sure that it remains capable of preventing anything going over 10 bar. And therefore, it's identified as being, critical to safety in that sense. Process control systems are next, and in here we will put things like control loops, keeping the pressure down by feeding in a particular reagent at a certain rate, which means you don't get a reaction runaway. That might go in there. Interlocks, hardwired systems, alarms. So you've got, so if the pressure goes up and you've got an operator response that's documented, and critically the operator has time available to him to do something about it, that can go in there. Physical protection systems comes next. Physical protection systems are things like relief valves or bursting discs, things that don't require energy to operate. And if you do want to cite them, I shall ask you if you look after them, if you take them out and make sure that they're functioning as they should do from time to time. And then the last one, which is usually where we get an awful lot of entries, is the people and procedures, what people do to prevent or to mitigate things from happening, to reduce the consequences or whatever it happens to be. And the reason for separating these out like that is because they have different levels of robustness in terms of being considered a safeguard or not. So if you do your analysis and you've got nothing in the inherent safety, nothing in the process control, nothing in the physical protection systems, and everything in the procedural things, it's not as robust as having a little something in each one of those boxes. It's just not as strong. Procedures and so on are not as strong a safeguard as a relief valve. And you get more credit for having physical protection systems, control systems, and so on. You get more risk reduction for having those in. So once we've got the safeguards in place, we know what they are, we know if there's any gaps there, and we know where you've been spending your money. We can see now where that money is actually giving you the most benefit, because we'll recalculate the risk in terms of the residual risk, how good those have been, and therefore whether you need to spend a little bit more money or whether your risks are as low as reasonably practicable. If we think there is something else that we could do reasonably well, we'll record it as an action, and you'll get a list of actions which you can complete. We'll also classify these residual risks in terms of whether they're high, medium, low, to give you some indication of priorities for completing those actions. So it's a very good way of doing it, I think. That split of safeguards gives you an awful lot of extra information as well. These causes of initiating events, I also find very, very useful. Usually I put in there things like human errors, mechanical failure, control systems, generics, because if you find out all of them are caused by human error, it tells you that some form of human reliability or safety critical task analysis might be applicable. It's all good information to get out. It all integrates with your process safety management system because it filters throughout. It has tendrils that go out into all the other things that you do on site to reduce your risks. Okay. Typical deviations that we use. The overpressures, the underpressures, overfilling, losses of containment caused by, for example, hose failures or temporary piping, those kind of things, impact damage by forklift trucks, that kind of thing. It's not a huge list, is it? It's however you work, and this is why it's I sometimes refer to it as quick and dirty, but it isn't. It's quick and rigorous is what it is. It just takes less rigor than some of the other studies that you might undertake. A quick caveat though, please don't forget those times when your plant is not performing your day-to-day activities. So things like startups and shutdowns become important. These are things that are not, you don't do every day. They can be once every 20 years sometimes, but startups and shutdowns typically more involved, different processing that goes on. And very often you might have more manpower and therefore more people that you can hurt following loss of containment. So yeah, remember that. Maintenance should be in there as well, both in terms of a cause, i.e. you don't do any maintenance, and in terms of a safeguard. We know this isn't going to fail because we check it twice a week or however frequently you do it. So think of those things as well. And also you might be running some trials when you are going outside your safe operating envelope. Is that going to cause you an issue? So bear in mind those times when you're not performing your normal day-to-day activities. In terms of the causes, that's this box here, the cause and initiating event. I'll take you through the prompts, but it's up to you to identify what the initiating events are, or the causes are, because it's your plant and you're the people who are operating it. So it's your expertise on which I am going to rely. You can be as imaginative as you like, but we will discuss all of them. And if it requires Jupiter and Saturn and Mercury to align before a particular accident could happen, we might dismiss it as being incredible. However, if a couple of things need to go wrong, it's still worth describing as this so-called double jeopardy. It's still worth looking at because we might find that there is a common cause for those two failures to happen simultaneously. So I always like to explore, and that means letting you be imaginative and having a little fun with it. Some examples here. Over under pressure, we could have blockages in condensers. I was doing a hazard yesterday, and that was exactly one that we came up with yesterday. Overpressure could be caused by an explosion. Under temperatures or changes in temperature, heating or cooling failures, or a runaway reaction, these kind of things. But these are the things that we would be looking at. Overfilling, human errors, very common. Failure to empty vessels, and then you put another batch on top of it. Impact damage from cranes, forklifts, hoists, those kind of things. And maintenance, whether it's preventative maintenance, cleaning, scaffolding has gone in there as well. That was another feature of yesterday's hazard. So all sorts of things. There are some other examples here. I don't intend to go through all of them, but these are the things that we will go through as a guide and say, do you have any issues with vibration? Is that something that might be an issue in the future? Is it small bore? Is it rotating machinery for which balancing is required? That kind of thing. See another page there. So I'll just come back to this because in terms of initiating events, I usually find it's the operator who is the most important person in the room. They are usually the ones with the most to say about initiating events because they've seen them. They've seen what can go wrong because they deal with the equipment day to day. It's not only their knowledge that's useful, it's the knowledge that we impart to the operator as well. So I mentioned earlier that these were good as training exercises. It helps the operator because it tells them why they are doing things the way that we are asking them to be done. And from our point of view, from the people running the study, we need to know what actually happens against what it is that the designers intended, whether there's any difference, because that difference can inform the designers. And it can mean changes for later on as well. If we suddenly discover that the procedures haven't been updated for 15 years and that they're now no longer applicable, that's important information to get out. Even though the plant has been running perfectly happily, that's because the operators have accommodated that. This was one of the features of the Texas City incidents where procedures are out of date, but it's one of the ways in which we discover that might be the case. And they usually have a good knowledge of past incidents as well. Usually, well, the last time it happened, they will say, this happened, or so on. So always get the operators involved. The scenarios that we get, a full description, as much detail as necessary. It's a live document. It's going to be reviewed by other people at a later date. So make it as easy as possible for people to understand what is intended. Will the reviewer understand what was meant? The consequences need to be the worst case consequences. So if you're losing from a dead-headed pump, what is it? What is it that is lost? Is it hazardous? Is it flammable, toxic, or dangerous to the environment? How many people might we hurt as a result of that? We're going to assume that ignition occurs very frequently as well. Is there going to be a pool fire, a jet fire, flash fire, or something that we call a vapor cloud explosion? Whether that's confined or unconfined, that's going to give us an indication of how damaging it's going to be. How many people are going to be in the area? It's down to the team to tell me whether this is going to be true or not. If it's just a couple of people, perhaps an operator and an assistant, or whether it's on a remote tank farm where there's nobody around, those are all important to what the consequences might be. We don't consider protective systems or mitigation at this point. So we need to record instead the number of fatalities, the number of major injuries, the damage to the environment that we could possibly do. So I come back to this. Don't be overly concerned about recording severe consequences. We are telling a story. We know that there are severe consequences because we've got dangerous materials on site. Those have consequences if we let go of them. And the reason we don't let go of them is because you've got decent safeguards. So consequences, of course, can be modelled as well. And this is another thing that, well, if you give me a ring, I can do it for you as well. We can calculate the distances to particular criteria, whether that be a level of radiation that might hurt people, so heat, or blast over pressure, or distance to a particular toxic dose that people might be subjected to. And it's sometimes very useful to do this, in particular where you've got a particular vulnerable population at risk. So if your plant is sited right next door to an old people's home or a school or a supermarket, you've got a vulnerable population who may be at risk from your activities. We need to recognise this. It's going to define how good your safeguards need to be. You can also record the consequences in terms of the damage that it's going to do to your reputation as well. So this is not required under the law, but it's sometimes useful for companies to do that. If a particular loss of containment means that you're going to lose £1 million a day, that might be something on which you want to spend a bit of time thinking about. So just these last little bits about hazard and risk. Sorry, I missed the title. There we go. Raw risk. There we go. Risk is a combination of things. It's a combination of how often things are going to happen and how bad they're going to be. So that's the consequence, the number of fatalities, the amount of harm that you can do versus how often you do it, the frequency or the likelihood. And it's this combination of likelihood and hazard or consequence that gives us the frequency. So we have some predefined criteria for deciding what these are. The risk tolerance criteria, the risk matrix, we have one for both people and the environment. It's a fairly subjective estimate, but it should be an informed decision, and we'll give you some guidance on what that is. This is our breakdown. The numbers are what they are: once a year to one in every 10 years, 1 in 10 to 1 in 100. So it's an order of magnitude difference that sits behind those numbers. And this is very useful to do. Actually, we've actually characterized in terms of a qualitative description. So 10 to the minus 2, 10 to the minus 3, 1 in 100 to 1 in 1,000, possible to occur during the lifetime of the plant. Likely you have had root causes. And that's sometimes a little easier for people to deal with in the meetings rather than the numbers. So I do use those quite frequently. And then we can plot it on something like this, a risk matrix. And this is really our decision-making tool. It is calibrated. It is calibrated to a publication called R2P2, Reducing Risks, Protecting People, which is on free download from the HSE's website in the UK. And it is calibrated to a single fatality. And the boundary between what is, well, we've characterized this as high, medium, and low. In the R2P2 document, this is intolerable. The boundary between intolerable in the red and tolerable if a LARP or as low as reasonably practicable for a single fatality is set here. That's the boundary, and that's 10 to the minus 3, or 1 in 1,000, or a 1 in 1,000 chance per year of suffering a fatality if you are a worker. If you are a member of the public, you get an extra order of magnitude risk reduction. So that takes you from 10 to the minus 3 here to 10 to the minus 4 there. So that's the boundary between what is intolerable. If you calculate that the risk associated with the scenario is greater than that, you are working illegally in the UK. You must stop, put in place some risk reduction measures and reduce the risk to, first of all, a LARP, and then, if you can, to below 10 to the minus 6 or 1 in a million. And that is considered broadly acceptable. So that's a very, very useful thing to do. There's one for the environment as well. It works in exactly the same way, but the category is for a MATI, and that stands for a major accident to the environment. And that's my boundary there, 10 to the minus 4 for a MATI. This is the publication. This is known as the risk tolerability carrot. We have an intolerable region at the top and a broadly acceptable region at the bottom. And this is my boundary between what is intolerable, broadly acceptable, and tolerable if a LARP. And together, once we've got the risk identified in terms of those severities and likelihoods, we've now given ourselves an ability to put ourselves on this diagram, to put ourselves on this risk matrix, and therefore define whether, or decide whether we need additional safeguards. And given that the safeguards are these, if we find that there is a gap in the physical protection system, that might be the place to aim your safeguards at. It shows you where these gaps are. It might be that you don't have a procedure for dealing with deliveries. That might fill the gap that you've got to bring that risk down. It might be that you've got a process control system that isn't doing the job it's supposed to do. That might be the place in which to spend your money. So whether you're looking at a new plant, whether you're looking at an existing plant and making improvements, it is this technique, I think at least, the HAZID technique, that gives you the best information, the quickest, the most useful, and fulfills your requirements in terms of demonstrating that you've reduced risks to as low as reasonably practicable, therefore that you are complying with the law as well. Okay, well, it's just coming up to the hour. I could go on like this all day, to be honest, but I know there's a lot of you have a lot of work to get on with. I know I do. So I'd just like to thank you all for your time. It's been a great pleasure talking to you. If you need anything else, for example, let's say that you need a HAZID doing, please get in touch with us. We'd be more than happy to accommodate you. I've done a lot of these over the last years. I've been doing this since the late 1990s, and clients like them. Clients like the approach. It does give you good information. They can see the value in it. I think that's the key thing. They can see the value in it, provided they've got all that information that goes into it and the wherewithal, the operators and the so on, to actually furnish the meeting. But it is a good technique, and I do recommend it. But in the meantime, thank you very much for your attention. I've enjoyed it. I hope you have as well. So hopefully we'll see you at the next webinar. So take care, and thanks very much. Bye-bye.